So in the lab we had a bottle of hydrochloric acid, and it said that its concentration was somewhere between 30% and 35%. Now that's a fairly big and fairly imprecise range. So the purpose of this titration is to determine much more precisely how concentrated that hydrochloric acid is. So we're going to use sodium hydroxide, which is the base that we're going to titrate the acid against. We know that this sodium hydroxide is 0.100 moles per litre. So we know the concentration of the sodium hydroxide very precisely, and we're going to use that to determine the concentration of the acid. Now, a particular point for titrations, it's more important with this older burette which has a ground glass tap, but even with modern Teflon taps, do not put sodium hydroxide inside a burette because it's corrosive. It will eat and destroy the tap. So the sodium hydroxide therefore definitely has to go in the flask, not in the burette. Now, one of the things I'm going to try and do is talk about why I do each of the things I do. So in terms of measuring things and cleaning things and what we do, I'll explain what I'm doing. So first thing I'm going to do is wash the flask, and I wash the flask with deionized water. The reason is I'm going to add a known amount, using the pipette, of sodium hydroxide to the flask, and I know the number of moles that I've added, and so I don't really care if I dilute it a little bit, because what's important in the flask is the amount of the substance that I've added. So that's the known piece. I'm going to, in a moment, rinse the burette, and I'm going to rinse that with the acid, because what I care about for the acid is the concentration. So if I were to rinse it with water and then put the acid in, I would have diluted the water and I would no longer know what the concentration is, and so my whole experiment would be wasted. So everything we do has a reason behind it and an explanation for the reasons we do things. When I fill the burette, I'm going to use a funnel in the top. I'm going to fill it, and then I'm going to make sure to take the funnel out, because otherwise a last drop of liquid from the funnel could drip down into the burette and change my measurement. So each of these things has a meaning and a purpose. So very quickly, I'm just going to wash the flask with deionized water, make sure that there's no contaminants from before. I will wash the burette while I'm at it. So I need to make sure I have the right thing, which is the acid. I'm going to put a little bit of that. I'm going to do that over the sink, so I might disappear out of shot, but I'm just pouring a little bit of acid into the burette. And just swirling it around, running it through the tap. Actually, I can do that. Swirling it around, running it through the tap to make sure there's no contamination inside the tap and the tap is full, and pouring some out the top to make sure that the only thing in this burette is hydrochloric acid. Now, once I've got it back in place on the stand, actually, let me rotate it that way so you can see the gradations on the burette. So let's fill that. Now, what students often try and do, and what you might try and do is, or try to do, is fill it to a very precise number. But that's a losing game because things will run down the side and so on. So what you want to do is fill it to a random number and then measure it very precisely. So in this case, I'm going to be very careful as well, because there's a lot more volume in the funnel than there is in the burette. So you need to make sure the tap's off and fill it, and I'm going to fill it to about eye level. We've got that placard which helps with setting eye level, but I won't use that. I'll just go by eye. But I think that's going to be enough for my purposes. I don't need to completely fill it. I will make sure I take the funnel out. I will flick it a bit to get any drops down from the side. And then I will determine and carefully measure looking at a flat angle, and I'm having to do it backward, but it's 17.57 millilitres is the initial measurement. So the final measurement will be somewhere down here, but I need to note this initial measurement. So 17.57 milliliter is the initial reading on the burette. Now for the flask, I need 20 milliliters of the sodium hydroxide. In the olden days, we used to pipette by mouth, just sucking it up. That's not particularly smart, particularly with sodium hydroxide, which is corrosive. This is relatively dilute, but still not great. And certainly for pipetting by mouth other stuff, it's a really dumb idea. So in the modern world, we use these. There are even fancier and more electronic and technical looking ones than this, but this pipette filler, and I won't give you the full pipette filler lesson, but there are three little bits you can press. One to empty the bulb, one to fill up. The one to fill up starts with S. I don't know what the S stands for in that context. And with this, what I'm doing, there's only one gradation on a pipette. It's that one line just there. So I filter just above it, and then I'm going to use the third one, the E one, to release the liquid until the meniscus is just at that line. Oops, slightly overshot, so I have to fill again. Just a tad. And release more slowly until the meniscus is just at that line. So now I know that I've got exactly 20 ml of sodium hydroxide, and I can hit the release and release that into my flask, my clean, freshly washed flask. If I get impatient with that, I can also pop the filler off, get a bit more water flow, a bit more air flowing in the back, and flow that out. Now, most pipettes are designed to just be touched to the surface of the liquid, just to use surface tension to pull out that last drop. But if there's any left after that, leave it there. That's how it's designed. It's designed to tip to the water and then be left at that. So, okay, we've now got one colourless liquid in the flask and a different colourless liquid in the burette. So how are we going to know when we've got the exact same amount of each of the two in the flask? We need an indicator. So we need to know how acidic or basic the solution is, because we have a base here and an acid here. What we're trying to do is neutralise. We're trying to neutralise all of the base with the acid so that we know that end point, because then we know we will have used exactly as much hydrochloric acid as we have sodium hydroxide, and then we'll know how much hydrochloric acid we have, and from that and the volume we can calculate the concentration. So this is phenolphthalein indicator. We only need a couple of drops. It turns bright pink in base. So I'm putting it into the sodium hydroxide, and you can see that it's a bright pink colour. I'll put it above the white tile for clarity, although I have to recombobulate things a little bit. Now, you can see that phenolphthalein, when it's in neutral or acidic solution, is colourless. So we're going to go from this bright pink colour back to colourless, and we'll know that that's the end point. Now, with this, these ground glass taps, what you should normally do is reach around from the other side to help hold the tap in. It's less of an issue with modern taps, so don't worry about it too much. But what we typically do, and I'm going to spin this around now that you've read the reading, is for right-handed people, right hand for swirling the flask, left hand for the burette. Use whichever feels comfortable, and if you're left-handed, it's the other way around, but that's the way we usually do it. And what I'm going to do is, I know because that acid is 30 to 35%, it's going to take about the same volume as the 20 ml of sodium hydroxide that I used. So if I didn't know, if I had no clue how much it was going to use, I'd probably have to go very slowly, drop-wise all the way down. But I know that it's going to take somewhere on the order of 20 ml. It might be 15, it might be 25, somewhere in that ballpark. So I can run some down reasonably quickly. And just watch swirling. Oh, I can see that it's going clear and then coming back. So I need to slow down. So as soon as we see it approaching that end point, we need to slow down and start going by small bits or a small drop at a time. So I'm adding just a small amount, and you can see it goes clear and then kind of goes away again as I swirl. So we're getting toward that point, and I've got to be really careful. You can see it might be paler overall now. This is not a particularly cooperative tap either, but so we're just going a drop at a time, or a couple of drops at a time. And what I want to do is get right on the end point. It's colourless in acid, so I could dump a whole bunch in and it would go colourless and stay colourless forever, but then I would still have no idea where the end point is. So I've got to try and sneak up on the end point at the point where it just one extra drop switches it over from pink to colourless. Being a little bit bolder now, and of course, while fortune favours the brave, you can also come very unstuck. Whoop! Yes! I think that's very slightly overshot. You can see it's still not completely colourless, but I think it's gone very slightly past. But we will measure it and record that one. That one is 36.60 millilitres. 36.60 is, we were at 17.57, so if my maths is any good, that's about 19 millilitres. And that's pretty close to the about 20 millilitres that I suggested would probably be the number. Now I did slightly overshoot. You get ridiculed for doing that in the lab, but we do also have finite time while we're recording. I'm happy to leave it at that one and to do the calculations on that result and determine the concentration of the HCl, the unknown hydrochloric acid, on the basis of that measurement of the reading in the burette of the amount of HCl that it took to just neutralise 20 ml of 0.100 molar sodium hydroxide. G'day all. Our quick calculation for our titration video. As ever with this, if you were doing the real titration in the lab, you would do multiple trials. If you overshot slightly, as I'm pretty sure I did in the video, you would go back and try again, and you would have several trials to make sure that you hit right close to that end point where it turns, and that you were consistently hitting that same point and writing down your results. But in our particular case, we had, let's see, we had NaOH, sodium hydroxide, with a known concentration of 0.100 moles per litre. We had some hydrochloric acid with an unknown concentration. Now, I think I may have misspoken in the video and said that it was 32%. That's not accurate because 32% hydrochloric acid is 10 molar, and 0.1 molar would be the wrong thing to calculate it with. What I should have said was that the bottle said 30 to 35% or 30 to 36%. Tracy made it up as though it was 32% because that's the usual standard. So what we're really trying to find out is, was it 32%? Did she make it up to be exactly 0.1 molar, or is it slightly different to that? So we can work that out. So the neutralization reaction is essentially NaOH plus HCl gives NaCl, table salt, plus H2O. And in this, really, the sodium ions and the chloride ions are spectators. So salt is soluble, there were no precipitates, so basically you had Na plus and Cl minus ions in solution at the start of the reaction and also at the end of the reaction. They didn't participate. So we could actually ignore those completely, and we would have OH minus and H plus gives H2O. So that's the real neutralization reaction. We had some OH minus and some H plus, and we need to balance that, don't we? No, we don't, because we have an H and an OH, so we have 2 hydrogens, 1 oxygen. So that's already balanced, which is nice and convenient. Now, we found, we actually measured out 20 mil in the pipette of the sodium hydroxide. So we know that concentration is measured in molar or moles per litre, which means a number of moles divided by a volume in litres. So we can rearrange that to find the number of moles of sodium hydroxide that we had. So N equals C times V, multiplying both sides by V. The concentration was 0.100 because we made it to be, and the volume of that was 20 millilitres, which is 0.02 litres. We should work in litres because that's the SI unit, and that's in moles per litre, so that needs to be in litres to end up with a number of moles. And that number of moles is going to be 2.00 by 10 to the minus 3. Now, the volume of hydrochloric acid is found by, so this is just V. Let me do H plus actually. Oh no, let's do HCl. The volume of hydrochloric acid is equal to 36.60. That was the end point of our titration. Minus 17.57. That was the start point of our titration. So that's 19.03 milliliter, which is equal to, I should put units, milliliter, equals 19.3 by 10 to the minus 3 litre. A milliliter is 1,000th of a litre, and we should work in litres. So now what we want to do is actually work out the concentration of our HCl. What we know is that the number of moles of OH minus and the number of moles of H plus are equal to each other because the reaction for the equation is 1-to-1, and we just exactly neutralized them. So there should have been exactly as much of each. So that N is just going to be that 2.00. We need to know how accurately we know it, by 10 to the minus 3 molar. So, sorry, not molar, moles. That's a number of moles. So the concentration that we're looking for, the concentration of the hydrochloric acid, C equals N over V. Number of moles we know because we just worked it out, 2.00 by 10 to the minus 3. Volume is actually our titer, so it's 19.03 by 10 to the minus 3. I mean, technically we should write that as 1.9 by 10 to the minus 4, but I can't mix up the two. So it's 19 by 10 to the minus 3 is the same thing. And if we run that through the calculator, we end up with 0.105 molar. So Tracy made it up to be 0.100. 32. Now we can actually work it out what the actual concentration was. So she made it up as though it were 32, but it seems to be bigger than we expected. So that suggests that the concentration was actually higher than 32. 32% hydrochloric acid is 10 molar. So 0.1 molar is 1/100th of that. So if we multiply this by 100, we will get, I'm doing this just by proportional reasoning. So it's actually just going to be 10.5 over 10 times 32%. Will give us the actual percentage of HCl that our HCl was, and that's 33.6. So it was up toward the top of the range that the bottle quoted, 33.6% rather than 32% HCl in the bottle. And now we know we could actually go back and place a more precise label on the bottle if we'd done the experiment more times and more correctly and more carefully and made it worked through our uncertainties and so on. But hopefully you've got a sense of the calculation for a titration, how it's done. So effectively we find out the moles in the aliquot. The aliquot's the name we give to the amount that we put in the flask. So we measured it with a pipette into a flask, a specific amount and therefore a specific number of moles. And then the titration against that means that either there's exactly the same number of moles of the thing in the burette, or there is some multiple if the equation is such that it's 2-to-1 or 3-to-1 or 3-to-2. So you need to work off the equation as well to check those proportions. And then we can work that out backward by knowing the volume of the titration to work out the concentration of the substance that was in the burette, which in this case ended up being 0.105 molar.